Okay.
Hey,
Welcome. Yep.
what do you plan to go over today?
Oh, hi, Matt.
Hey,
Yeah, so today my plan is to go over the content in this first machine learning book. So in general, this starts like super simple, just making sure that you have your proper versions for like SciPy and scikit-learn, really quick introduction to just using those packages as well. And then moving into just some really basic concepts of machine learning. So, we're not going to be touching on neural networks today. That will be like a whole other thing because there's so many layers to neural networks, no pun intended, that it really deserves some time on its own. So I really just want to make sure that like we start off with everybody on the same page. And for me, like the best courses that I ever took started where the material felt easy right away. And as you continue into more complex stuff, it gets a little bit harder, but at least you know that you started somewhere that you can approach it from. So today we're going to go over this book, Machine Learning Mastery with Python. I think Kevin's already gone into this book, and you can read through every single paragraph in this, but it's probably not going to be super helpful. I just wanted to highlight this here where they talk about learning Python machine learning the wrong way, and specifically point to here where it says deeply study the underlying theory and parameters for machine learning algorithms in scikit-learn. That you guys are really like dissecting every single deep learning algorithm and doing all the math with it, and it's fine and dandy and it's nice to understand exactly how they work, but from a practical implementation standpoint, you're going to have a much easier time just figuring out how to use the Python libraries and build up these codes yourself. So the approach that we always take to machine learning is first just defining a problem, figuring out what you actually want to learn about. So this is usually you have a data set that you have some sort of confidence in, and you want to analyze it to get some sort of answer, be that, an unsupervised learning where you're just kind of blindfolding yourself and looking for patterns in the data, or supervised learning where you can extract features from your data set and use it as something to predict whatever property that you're interested in. So the first thing to know is that you need to define your problem. And then once you kind of know what you want to do, you want to analyze the data that you have. So understand what is the dimensionality of my data, where did the data come from, how can I actually like bring that into the Python environment, and plotting tools are really helpful for that so that you can understand the little niche of the data that you have. Preparing your data for machine learning is probably the most important thing. When we're dealing with like the ECG data in the hospital, it took like 85 to 90% of our time to actually weed through all of the data and get it into a form where we could actually input that into any kind of supervised learning algorithm. And like with Matt the other week, we just had a meeting looking at using machine learning to analyze images of microplastics and try and figure out what they actually are and create a tool to assign a label to what they actually are. But we kind of determined that the data set is like kind of scattered all over the place. They're bringing in data that's been put together by a ton of different interns and employees that they had, and they're still trying to consolidate all of that. So I mean, like, good data is gold. And if you have really good data, then that's going to make your life easier, because what you'll find doing this is that the machine learning, actually doing the code in Python, is not really conceptually difficult. They've done a really good job making it read like English, and just everybody's using it. So there's a lot of tutorials online on how to do it, and they've really consolidated a lot of the workflow into just a couple lines of code. So we'll go through that, but if you have really good data, then that's the most amazing starting point to be at. Going from there, you need to be able to evaluate how well your machine learning algorithm is working. So we'll talk about descriptive statistics that you can use to measure the various ways that it's performing well or not so well, and be able to compare them together as well. And then there's always, how can I improve the results? So a lot of people will, just loop through a bunch of different machine learning algorithms and try and pick the one that seems to work the best. You got to look and see if you have any overfitting or underfitting going on. And I mean, we'll get to all of that, but it's important to be able to not only interpret the results of the machine learning, but also be able to identify ways that you can make it better. And then, of course, presenting the results. So once you're done, you have your finalized model, and you can start validating it on new data. So that's the overall kind of scheme that we use to approach these problems. And I hope to get there within the next couple lessons coming in here. Does anybody have any questions before I start diving into any code? Okay. So I will just go ahead and dive right into code here. So what I recommend doing here, if everybody has this drive set up here that I sent around last week, what you'll find under the textbook folder here is Machine Learning Mastery with Python. And I would just make a copy of this whole folder and store it somewhere on your computer locally. So be that like on your desktop or My Documents or on your Z drive, if you're always using it inside the lab, then that's a really good starting place. But within this folder, you have the PDF, which I was just showing you. And then there's a code repository, which I'm going to be going through here. So you can open these and follow along with me and put your own comments on there if that's what you want to do. And these are fantastic because you can open any of these files and they all just run by themselves. You don't have to modify anything, and it's going to give you all the syntax that you need to put different pieces of the puzzle together to solve whatever problem that you're interested in applying machine learning to. So I've gone ahead and done that. And I did it in this drive. So in this directory here, the Machine Learning Grant Lab one, you'll find Luke Python scripts, and I've just made my copy over here. So when I make comments and stuff on it, you can go ahead and go into here and just look at the files that I've changed as well. So the first thing that I'm going to do is I'm just going to take these and drop them into my Python editor over here. So everybody's using Spyder, I hope. It's basically MATLAB, but it runs in Python, and I really like it. I definitely recommend everybody to use it. And these first two scripts here are super simple. They just make sure that you have the packages installed that you need for doing this. So if I run this first one, sklearn version, all it does is it just prints the version of scikit-learn that I have. So I'm on 0.24.2. This isn't super important. As long as you have like 20 something, then you're probably fine. You may have exactly the same version as me, you might not. And then this SciPy versions over here looks at other things like SciPy, NumPy, Matplotlib, and Pandas, which are main packages that we're going to be wanting to use. So these are the versions that I have here. The most important thing, I think, is that you're running Python 3.6. I think 3.7 is also okay, but 3.6 seems to be kind of like the consensus package that most people are using for machine learning. I think a lot of things have been outdated in 3.8. Like I think TensorFlow has like really iffy implementation in 3.8. And in particular, 3.6 is supported by LabVIEW. So any machine learning backends that you may want to integrate into LabVIEW routines, if you write them in 3.6 here, then you'll be able to import those really readily. So that's all of chapter 2 in a nutshell already, and we could move to chapter 3. So we're going to move really quickly through this. We got a couple crash courses here. So, okay. So we got a Python crash course, which I'm just going to fly through over here. So start with strings. So strings are encapsulated by quotation marks like this. There are texts that you can edit, and you can index them in this way with the square brackets. You can say how many characters there are in it with the length function, and you can print it as well. For numbers, you have decimal points. There's a floating point number. You have integers over here. And what I'm going to do is I'm just going to run this whole thing. I think it's a little redundant for me to go through all of this syntax here, but I'll use this as an opportunity to point over to the variable explorer, which I really like. So this is definitely the most important feature of Spyder over any other Python IDE, is that it gives you a physical representation of the data that you have in memory. So you have lists over here, which is really nice, and you can sort them by value, and they have the indices over here, which will change. It gives you the data type and the size of each of these. So this is a list here. They have dictionaries, which in other programming languages, people call hash tables. The name kind of goes all over the place, but basically you say, I am giving this value here to the key A. So when you look up A, it'll spit out the value of 11, and so on and so forth. I guess one important thing here in for loop, so this range function basically takes in a number 10 and will spit out a array with 10 elements in it, or up to this number basically. And it's up to but not including this. So I believe this here is that printout. So you'll see it goes up to 9, and then it does not print out 10. So that is the fastest Python crash course that I've ever given. Definitely go back to this if you need a little bit of syntax, but I feel like everybody here is at least at this point. So I'm going to leave this for now. NumPy is the numerical package that is most popular with Python, and we're going to use it for just about everything. What a lot of people will do is, instead of just importing NumPy like this, you'll import NumPy as NP, and then you would do something like NP dot array of my list. When I'm doing physical implementations of the code myself, you'll see me use this notation just because it's a little bit more condensed, and it just looks better. Everything that you see online is going to be like this. So I'll keep it consistent doing this when I do my programming, but I think that as we go through the Python codes that are supplied by this book here, it may do numpy dot something, but just know that it basically is exactly the same thing. So I will run this code here. So you can define a list, and then you can convert the list to an array, which is actually really nice because the arrays are much more powerful than lists for numerical manipulation. So you'll see this is my list over here. It's in fact, in Python language, a list of lists. You have an outer bracket here, and then a comma here separating two inner lists. So if I open this, you'll see the first list here, and then the second list. But then if we look at the NumPy array implementation of it, you can see that it's presented more like a 2D matrix. And that's what you're going to be wanting to deal with, because lists are clunky, but sometimes you do need to use a list, and we'll get to those as they arise. You can access elements of the array by using this square notation here. So 0 is the first element. These are 0 indexed. You can look at the last row of it by doing this -1 implementation here. And then you can look at individual sub-elements by, it's always a row and then column. And then you can use these colons here to take an entire row and a specific element here. And I'm sure that you guys have used this to some degree. So I think I will move on from here because NumPy is pretty basic for Python. Pandas is something that you're probably not quite as familiar with. It's basically the package that you use to interface with Excel files and have tables to work with. So what they will do is the standard package that you get inside of Pandas is something called a data frame here. And a data frame is just like an Excel spreadsheet. So you'll have a bunch of columns, which are labeled like this, and then a bunch of indices. Sometimes these are numbers. It looks like you can add names to the rows, which I basically never do, but it's technically possible. And you can access them in this kind of way. So my data frame at 1. I really like using pandas. When we get a little bit further on, I have some more like kind of complex things that you can do where you can go through an entire data frame and select like sub elements that meet the requirements that you're looking for. But we'll get to those when we get to those. And then the final module here is matplotlib. So this is the typical implementation that people will do. They'll import matplotlib.pyplot as PLT. And instead of doing this every single time, you can see why they do it, because you just end up with PLT. The syntax for this is basically exactly the same as in MATLAB. So you get like plt.plot my array. I wish this wasn't coming up every time with suggested stuff. Plt.plot, X label, Y label, and a nice thing that's implemented in Spyder itself is that you can, instead of having your plots in line in the terminal here, you have a plot window over here. And that's nice when you have multiple plots. You can just click through these. You can save these plots in this way. You can save all of the plots if that's what you want. And you can actually copy it to a clipboard as an image. So you can copy and paste it into like Microsoft Word or PowerPoint or whatever. So I use this as kind of like a quick and dirty way to make results slides. And in PowerPoint, I'll just copy it directly from the terminal and paste it in a PowerPoint. So that is chapter 3 in its entirety. I think I'll take a minute here to ask if anybody has any questions about this. I'll open the floor. I think we're all good. That's good news. We're not stuck on the 3rd chapter. So let's see, chapter 4. Okay, so chapter 4 really just gets into using pandas, which I think is actually really nice because it allows you to interface with real data. And I will drop all of these here into Spyder. So there is this Pima Indians diabetes data.csv. So this is a data set that this textbook uses a lot. And essentially it has a bunch of variables that are correlated to if they have diabetes or not. So this is a classification problem that they go through. And the definition of classification is you're basically like trying to put a label on something. So in this case, you assign a 1 if they have diabetes, and you assign a 0 if they do not have diabetes. And the goal for all of these classification algorithms, which are supervised learning, is to take in this data for each patient and use some sort of model to make a prediction of whether or not they do or do not have diabetes. So I think in the next like 5-6 chapters, it just continues to use this syntax or this data set over here. And it looks bad as just the CSV file, but that's what it looks like. And we will load this up into Python over here and have a look at it. So apparently you can use NumPy to import a CSV, but I don't recommend doing that. So we're just not going to. And you can import CSVs with the CSV package as well. I do this sometimes just because things don't work with pandas, but basically I recommend just using pandas to import everything, because once you have a data frame in memory, it's just way more powerful and you can do so much more stuff in it. Okay, so I'm going to start with this one here. So we have this read CSV package here, and that's a function from pandas. So we define the file name here, and finally we have some labels for all of that data instead of just looking at that comma separated thing there, which is a little bit of a nightmare to look at. And yeah, here's our data frame. So this is much better to look at than that CSV file over there. So I don't know what these labels actually are, if they got a pedicure or not. The age one is pretty good. Test skin something. I don't know how they quantitate skin. But whatever, these are all the variables that they have here. And then most importantly, this class section over here. So this is whether or not they have diabetes. And this is the syntax that we're going to use for loading data into Python going forward. Apparently, you can load CSV data from the internet. So it looks like that's what you could do here. I didn't know you could do this until I started looking through this. So if I put in this link here, I think it doesn't like having the quotes here. I just put in this link. It's literally just that CSV file that's hosted on this guy's GitHub. I think that's just like a forwarding link or something. But this works very much the same way, where you can put in the URL and then names, which is the column headers for each of these, and you end up with the same data frame essentially. So that's kind of cool if you have something online, but like 99.9% of the time, you're just going to have a CSV file that you have locally, and you're not ever going to use NumPy to load files from the internet. So I'm not going to look into that as well. This is the only file here that is actually important. Load CSV pandas. Does anybody have any questions about loading CSV files with Python? Okay. We're just flying through these chapters here. Chapter 5, let's go. All right. So I'm going to drop all these guys in here. Head.py. Okay. So this one here is just a little bit of syntax. So data is the actual data frame that has all of the CSV file information in it. And it looks like if you use data.head with 20 as the argument going in there, it will assign a new variable that has just those 20 rows that are inside of it. If you print that out, then it gives you kind of like a peek, as they say, into the first little bit of your data. So that's just a little bit of syntax that you can use. So that now we're starting to get into that analyze data part of this. So essentially you have your data, it's loaded into Python. How do you actually visualize it, and how do you actually understand what you're dealing with? So here, if I run this file, so this is class distribution.py. I'm just going to open up a new console here. I run this, then what this goes through and does is it counts the number of people that we have in each class. So if we look at this data frame here, we have this class label, either you're a 1 or a 0. and we have a total of 768 patients. And this essentially just goes through and counts all the different classes. So we have 500 people that are negative diabetes, excuse me, and 268 people that are positive diabetes. So this is really kind of the first thing that you want to know, is my data set balanced? So when you're doing supervised learning, it's generally recommended and it works best if you have a balance in your data set. So you want roughly the same number of positive and negative label examples in your data set for that training process. This one I would say is slightly imbalanced. So it's kind of like a 2-to-1 ratio of 0 label to 1 label. I'm sure that it will still work. This isn't like outrageously skewed, but you start running into problems where you're looking to diagnose like rare diseases, for instance, where the prevalence in a population may be like 1% or less. And if you're just sampling the entire population, then you may end up with like out of 100 samples, like 97 samples that are negative and 3 that are positive. And you start running into problems doing machine learning when you have such a crazy imbalance in the class. 2-to-1's not so bad, and this is definitely fine to work with. So let's see, I'm going to go to Skew here, and I'm just doing these in no particular order. Let's run this file here. So Skew, is there any plots going on here? So this is data.skew. So it looks like it is telling you the skewness of this data. I don't know how important this actually is. The skewness is the third moment of a distribution. So the first moment is the average. The second moment is the width, or the variance standard deviation. And then the third moment is the skewness. So that's like how much data is in the tails of the distribution. And what this is telling you is if it's positively skewed, that means your data is skewed to the right. And if it's negatively skewed, then it's skewed to the left of the mean. This is interesting depending on the type of data that you're looking at, but I'm not going to look at this anymore. Data types. So let's see. So this is actually really nice to know. So for each of your classes over here, it lets you know what the data type actually is. So there's 2 different data types that we have in this data frame. So we have integers, which this is represented as int64. That's a little bit overkill. 64 bits for integers gives you an outrageously high integer that you definitely don't need to describe this data set. But I guess if we have a lot of memory, we can do whatever we want. And then for mass and petty over here, we have these floating point numbers. So a float is just anything that has a decimal in it. Then integer is something without a decimal point. Typically for classification problems, you're going to want an integer label. So that's the most important thing. But supervised learning algorithms technically are very flexible with the data types that you can take in, and you want to design your input data to best reflect the data that you actually have. Dimensions over here. So let's run this. So the dimension of our data is 768 by 9. So we've got 768 patients, and we've got 9 bits of data per patient. So if I were splitting up my data into training data, so the actual data that you're feeding into the neural network to train on, like your variables, and then your Y data, which is your target. So that's typically the class. We would have these columns over here. Oops. These columns here as our input data, and then our output data would be this class over here. So in our case, the class is diabetes, but I think this is just very general. and then describe. So let's see this. I actually don't know what this does. Display dot width 100. Yeah, so it looks like they are just showing like a certain level of precision for each of these. This doesn't seem useful for me. And then the last one that we'll do here is Pearson correlation. Okay, so now we're starting to get somewhere kind of interesting. So Pearson's correlation is basically the R-squared value. So it tells you how linearly correlated two variables are. So what this is doing here is, so it's comparing one class's variables to another class's variables for each patient. So what you'll see on the diagonal here is that you have perfect one-to-one correlation between each class in itself, which you would hope is the case. But then in other cases, you'll see some that are weakly negatively correlated, maybe a little more strongly correlated over here, like 0.39, 0.437. And this is actually somewhere that I really like looking at the variables in the variable explorer because it's color coded. So you see on the diagonal here, values that are close to 1 are in purple and values that are close to 0 are red. So just looking really closely at this, I think the highest correlation is, it looks like whatever this preg variable is highly correlated to age. And then skin is correlated to test, whatever those numbers are. And this is actually really important because if you have two variables that are super highly correlated, then you may not really need both of those variables for machine learning because you're just giving kind of redundant information. So what you're really looking for here is you want to make sure that you don't have like a value of 1 in one of these off diagonal elements over here or something close to it, because you can just reduce the dimensionality of your data set, which you'll come to. This is why everyone's doing PCA and stuff, is you want to make the size of your input data as small as possible so that you don't have to take in a million different variables to try and predict one thing. If you can reduce the dimensionality of your data set, you reduce the size of, say, your neural network, things will train faster, you'll be able to make predictions faster, and you become less prone to overfitting as well. So that is everything in chapter 5 already. Any questions about chapter 5?
Yes, I had a question.
Yeah.
For the set option, precision, and tree.
Right.
So what's that for?
So I think this has to do with the fact that in these data frames over here, so this is our data, we have integers. Oh, you know what it is? This is just a display option here. So you'll notice here that the precision of these is 3 decimal places. And it's just making that the same for all of these. So why don't I just try to comment this out and see what it looks like. It looks like it's okay. I'm just gonna get rid of all these options here. I'll do it in a new window. It probably already has those options built in because I would run it again. I will run this. Oh yeah, that looks horrible if I take out those display options. So why don't I change the width first? And that's bad. And then putting this in here just makes everything display really nicely. So thanks to the author for making that look a lot nicer than it does without those options set there. Any other questions here?
Hey, just a little bit. If you go to the head.
Which one?
Go so. What's not here? Head.
Ed. Oh, dot head. Okay. don't see, is head one of the, where do you see head?
It was
Oh,
one of the
in
ones
the
that,
in the
it-
previous chapters. Oh,
yeah, it was
okay.
one of the ones that we did before that just shows the header, like the top 20 values or whatever you give it.
Okay. Like the peak one. Data types, head.py, got it. Okay, yes, this one. Okay. What's your question about this? Eric? Is anybody in the lab there able to?
Yes, Eric is having issues.
Okay.
He's back. Okay.
Yeah.
Zoom related issues.
Okay. You can hop on any one of these guys' computers over here as well.
Okay. I'm here now. So what I'm actually saying is that
Hey.
Stop.
I can hear you. Are you screaming in the lab?
So what I'm saying is that if you look at the C line,
Like if we're gonna talk to Sarah's.
Yeah, no worries. I'm looking here. Yeah, so I look at the sixth line. Yeah, data.head.
Wait, try again. What's your question? Do you want me to ask it?
It's actually trivial. Now he used this data.head to select about 20 first 20 rows. And you can also use column the quotations to select also the same 20 rows. Right.
Oh, like why are we using head instead of?
Yeah.
Okay, so you want to know why we use this notation. So this notation is actually really nice, and I don't use this notation because I didn't know it exists. And now I'm going to start using it because it's really nice. But basically what I would normally do,
Oh,
so I
you just said it was a notation. You don't know.
Hey, what did you say?
It's just a notation. So what you could do is,
Hey, look, what did you say? Sorry,
I just said it's a notation that they use. So it's actually really nice, this dot head function.
What?
Can you hear me there, Eric?
Yeah. It's okay. Yeah, exactly. That was what I was talking about.
Yeah. So an alternative way of doing this is I could go data.
You should move on. I can't even hear you. Yeah, you move on.
You can't hear me?
Okay. I can't even hear you. Just move on.
Is this button on for you?
Nah, this
I think it's a problem for you because I can hear me.
it's all right. It's already 100.
Yeah, and I can hear you.
Yeah, just go ahead.
So I have a question
I'll
now.
ask you later. Go
We're,
ahead.
Okay.
we're speaking about head. So head is the first 20 variable, but is tail exists? So it's the, for example, 20 last one?
Maybe. Let's see. Data dot tail. Let's look at the 20 last ones. Let's see if this works. Okay, all right. Peak too. Yeah, how about that?
Is
Yeah,
it?
that does work too.
Okay, okay.
Nice.
So head is really the first one. Okay.
Yeah.
Cool.
Yeah, that is good. So here you can look
Yeah,
at the last 20 elements.
Yeah, I need to log off and then log again. Maybe one person should use the audio.
Okay. I definitely plan to do these in the lab, and I think that's going to be a lot easier because I'll be speaking into the computer, but then you guys won't really need to like have the audio coming through or anything like that. But just in the sake of getting things rolling, I think this is the easiest way to do it. So if we're all good on this, let's see, are we in chapter 6 already? Okay. Okay. So I think that the next natural thing to do is do a correlation matrix over here. So I think that this is a lot like the Pearson correlation thing that we did before. So we'll see what this does here. Yeah, so this does the exact same thing as we did in the previous example here, where it just looks at the linear correlation between each of the variables that we're inputting for the patients. And I believe that it does a plot. And the color on this plot actually looks almost exactly like what it does in the data frame, which is nice. So I'll put the data frame over here and then the plot over here. And they look basically exactly the same. And you would hope that's the case. So if you want to visualize it with a plot, then over here is the syntax to do that with matplotlib. So we can look at box plots. Oh, and that's ugly. All right, let me show you my trick. So if you guys have used Python for longer than 3 minutes, then you'll know that it's really clumsy for plotting. There's a little trick that you can do to make this a little bit nicer. So I go pyplot.tight_layout. This syntax here, you got to make sure that it's actually before you use this show function. If I replot this, then it fits all of the labels and everything properly into the window that you use. So it's not disgusting to look at. You'll see me probably copying and pasting this a couple times if this continues to be a problem. But essentially here, you have a box plot. So a box plot has the mean value as the center in the box, and then this box around it. The box around it is the interquartile range. So basically the data that is skewed between the 25th and 75th percentile is encapsulated by the box. And then you have these whiskers here, which I think is 2 standard deviations away from the mean. And then outliers are labeled in dots here. It can be really helpful to understand your distribution in this way. So for instance, with the skin variable, you see that there's actually very few outliers, but with this petty one, you have a huge number of outliers in the data set. If I knew what these variables actually meant, then I could give you a little bit more context as to maybe why there's so many outliers here. But these box plots are a really great way to represent data for your input data, but also how well your machine learning is actually working. So a little bit later on, what you'll find is that we will use and compare a bunch of different machine learning algorithms. And since they're trained empirically, the results are not only the same, or not always the same. So you're always repeating this. So you'll have like an average and standard deviation associated with each machine learning algorithm that you're using. And box plots are a really nice way of comparing the performance of each of those algorithms. You can do a scatter plot of a matrix. And this is taken a little while on my computer over here.
Meanwhile, I have a question.
Sure.
So in correlation metrics and covariance metrics, so for off diagonal elements, I mean off diagonal cells, both demonstrate the correlation between each two component. My question is, what's the difference between the correlation matrix we have here and a covariance matrix?
Yeah, that's a good question. So this, I believe, so the covariance matrix is the variance of X and Y for each of these components, and that's what's used as the input for principal component analysis. So essentially you're looking at the covariance between two. So you're looking basically a variance between vector 1 and vector 2. Whereas the Pearson correlation coefficient, I believe, just looks at a dot product between the two vectors. So it's just looking for linearity, essentially. We'll get to PCA, which uses that covariance matrix, and that's actually really important for dimensionality reduction, because honestly, a lot of times you can have like a huge sum of data that you can reduce to like 3 or 4 dimensions using PCA. And I won't go into all the math of how that works because I'm sure that's been beaten to death in Roman's class, but I can give like the conceptual 5 steps of how PCA works when we get to it. And I think there is a code in one of the next chapters that does do PCA. So we'll look at it when we get there.
Okay, thanks.
Sorry, Metro, what was your question again?
So my question was that the correlation matrix demonstrates the linear correlation between each two components, while in the covariance matrix, it's just the covariance between two components like 1 and 2, while the diagonal elements demonstrate the variance between each two.
Okay, thank you.
Okay. So, so let's see this. Okay. This is a lot of data all at once. So let's see if I can make this a lot bigger. And I got a good computer and it is struggling here. There we go. Can I drag this? It did not like that. Okay. So what it looks like is happening here is on the diagonal, what it's plotting is just a histogram of the distributions of each column of the data. So you'll see that down here. And most importantly, for a class, you either have a label of 0 or 1. So either they have diabetes, which is a 1, or they don't have diabetes, which is a 0. Then you have like age, which is a continuous variable. So you see most of the patients are like around 25 years old, and then it tails off as age increases. Same with whatever this petty is. It seems like the weight is kind of normally distributed around 40 units. I don't know how they measure the weight here. That seems kind of slim. Maybe they're using stone. And then all these off diagonal elements here are showing the linear relation between them. So this is exactly, this is kind of like a scatter plot view of that Pearson correlation matrix. So I remembered there were some elements here that were close to the diagonal that had a pretty high correlation. You can see like a little bit of linear correlation between them compared to these, which is just like a huge blob of data. So that's just a way to visualize the data with a scatter plot.
Look, just out of curiosity, I'm here reading at the BIMA Indians Diabetes Database, and just out of curiosity, PREG stands for pregnancy, number of times pregnant, class is the glucose plasma, pressure is blood pressure, skin is skin thickness, S is an insulin test, mass no idea, petty is the diabetes pedigree, and age.
Okay.
Just out of curiosity.
Thank you. That is actually really valuable information. Did you find this in the textbook?
No, I just Google domain. Yeah,
Oh, okay. I guess it's probably a famous
Yeah,
data
it
set
is.
then that a lot of people use.
yeah, it's in Kaggle.
Okay, thank you. That is
Alright.
good. Skin thickness. I was like, how did they like put a number on skin? That makes sense now. All right. I guess moving on here, we've got, you can look at histograms. These are all the elements that were in that diagonal of the previous matrix. And then these density plots are, I guess, oh, these KDEs, is that what they're using here? Yeah, so let me do a tight layout on this because there is just way too much going on here. That's a little bit better. So coming back from the histograms that they used, you can fit a distribution to it, I guess, using the plot function and putting kind density into here. And it gives you kind of like a rough kind of Sharpie line distribution of what the data actually looks like. And I don't know how there's people with a mass of 0. That's a little bit weird. Maybe that's included in the data set just on purpose for outliers, but that doesn't seem physical to me. But I guess if you want to visualize the data this way, then it's possible to do that. So I think I'm going to leave this chapter at that, and then I'll move on to the next chapter here. Does anybody have any questions before I move on?
Yeah, sorry, just before you move on, not a question, but responding to Masha's questions. The Pearson correlation factor is the covariance between two variables divided by the standard deviation of each variable. So to answer your question, they're basically the exact same thing. Covariance
Okay.
and correlation, they're just different, scaled differently.
Okay. So that's actually really useful. So basically that Pearson correlation matrix that we have there is what you would have as the input matrix to PCA. And so PCA calculates this covariance matrix, but the first step of PCA is actually just standardizing your data set. So transforming it so it has a mean of 0 and a standard deviation of 1. And then the covariance matrix is already normalized to have a standard deviation of 1, whereas the Pearson correlation coefficient already does that implicitly.
There you go.
Okay. Anybody else?
Luke, what is subplot here, and what does it change if I put false?
Subplots equals true. Okay. That's a good thing to ask because I don't know what happens. I think it's just going to plot all. Oh, yeah. So
Okay,
I guess it puts all of
summit.
them on the same axis there, and it gives them a label in the legend here.
Okay.
It's really nice, this syntax, though, that you can just change something like that and it pops out for you.
Yeah, sure.
Seems to be a nice thing to have it with the subplots, though.
And so what is share x2? Why is it false?
I share x. It's probably so that they share the same x-axis.
Okay,
Yeah, let's see what happens here. It's definitely going to look super weird. Yeah, that is what it is.
Okay. Okay, and so density is just the plot model. Is it the name?
Yeah, so there's different kinds of plots, and you can always look in the documentation for this. Let's see, kind equals density. Maybe I won't find something in here, but you can change things to be like binned widths like this, and adjust these to like whatever you actually want. Density basically means that it's using the cumulative distribution function to draw a line instead of binning things like this. So what you'll find is like, depending on the width of your bin, you'll get substantially different values on the y-axis, because as you make the bins thinner, you'll get less number of data points per bin. But the density plots give you the overall shape of your distribution while maintaining a relatively normalized distribution value on the y-axis.
Okay, yeah, I understand.
Yeah.
Thank you.
Yeah, I guess the last thing here is if you, the property of the cumulative distribution function is if you integrate all of this, then you end up with a value of 1.
Okay, okay, sure.
Let me get rid of the share X. There we go. Okay.
And so when it's false, can you just delete the thing, or you need it?
When what's full?
The share X is false. If you just suppress the share X.
You may not need to include that. So if I come in here, I can remove that. Let's see if I run this. Yeah, so I guess it's just true by default.
Okay,
Yeah, so that's probably why it was included there.
sure. Thank you.
Yep. Any other questions before I move on to the next chapter? Am I moving too quickly? If I'm moving too quickly, anybody let me know. I was hoping to kind of get through all this intro, how do I use Python stuff as fast as possible, and then spend more time on the actual machine learning when we get to it.
Oh, it's a bit late to ask, but where can I ask you to explain once more? Where can we can I find the all material? Is that in Z Drive?
Yeah. So in email, I sent out a link to the Google Drive. Maybe somebody in the lab can help you set that up. But
Okay.
yeah, you can find that. I don't think there's anywhere on the Z Drive for you to copy this directly. I think the best way to do it is just to get linked onto that Google Drive, and then you'll be able to download it.
Okay, Google Drive. Thank you.
Yeah.
Thank
Are you setting up that brand new computer?
you. Not yet. Maybe tonight.
Okay. Yeah. Yeah, it would be good to set this up on there. So
Yeah, definitely.
yeah, because in here we have all the files that you need for installing Python for Windows. So we've got the
Great.
instructions and everything in here. So just install it like that. You'll be off to the races and in good footing.
Awesome. Thank you.
Yep. Okay, so we're in chapter 7. Okay, finally, we're out of displaying data and we're starting to manipulate the data a little bit. So we're moving on from, where are we here? From analyzing the data to preparing the data. So using data transforms in order to better expose the structure of the prediction problem to modeling algorithms. And we will start to do that here. Okay. So I will first look at normalizing data. Let me just rescale this window. Okay, so still working in this Pima Indians diabetes database. Essentially what we're doing here is the same as before. So we are loading up this data frame, and array is data frame dot values. So when you're doing machine learning, you're never going to actually insert the data frame itself as your input data. You're going to need to define a NumPy array as your input. It's only going to take in a block of numbers essentially. So that's what you're going to want to put in. So in data preparation, essentially what you're doing is trying to give it the data and answers. So if you look at the machine learning intro that I programmed here, essentially the way that conventional programming works is you have a bunch of data, and then you try and code a bunch of rules that take in that data and spit out the answers that you have. But what we're learning about is machine learning. So you have all your data. So this is your X matrix over here. And then your answers, which is labeled as your Y matrix. So that is if they have diabetes or not. And then given the answers and the data to the computer, you want to see if it can figure out its own set of rules, looking at the multidimensionality of the data that allows you to make predictions that go forward from the data to the answers. So the syntax in Python is typically X is your input data. So if I look at my data frame here, it's taking all of the rows. So this first index over here is just everything, all of the patients, and then column 0 through 8. So 0, 1, 2, 3, 4, 5, 6, 7. Python does this thing where it's up to but not including. So you end up with 7 elements over here, or 8 elements. And then your Y data is just this last column here, so class. So you have your X matrix, which is just basically all that data, just as a numerical matrix, and then your Y matrix, which is just a 1D matrix of all the diagnoses for each of the patients. For machine learning algorithms, they're really sensitive to the scale of the input. So the first thing that most people do is try and normalize it in some way. And the way that they do it in this book here is they extract this normalizer function from scikit-learn, specifically the preprocessing module, which makes sense because preprocessing is what we're doing right now. So the first thing that you have to do is create this scalar here. And then this scalar function, or there's this transform function over here that takes in the scalar that's defined by this and normalizes your data as such. So essentially what you end up with is this normalized X matrix where everything is, how is it normalized? I think it's to a length of 1. So this is the Ed Grant normalization, as we call it. So they call it L squared normalization. And essentially what that means is each of these vectors becomes unit length. And Ed likes to talk about this with his unit dimensionality sphere in hyperdimensionality space. But essentially all it means is that if you take all the values here and you sum up the square of all of them, it will sum to a value of 1. And that's a good place to start. It's really commonly done with Raman spectra. It's a really good first step to try to make sure that everything is normalized to the same Y scale.
So it is mean divided by standard deviation.
So this is, let me look up L2 normalization. And this is just a Python tutorial. I'm looking for an image. Aha, you asked for it, and we found Dirac notation. So this is why it's actually really widely used. Is it's the normalization factor in normalizing a waveform. So essentially what you do is if your vector here is X, so you have X1, X2, all the way up to Xn, your normalization factor here is the square root of the sum of the squares of that vector. So you square each of these elements, sum them all together, and then you get the square root of it. That is your L squared norm factor. So it ends up looking like this. X1 squared plus X2 squared, X2 squared, and then you get the square root of it. It's kind of like Pythagorean theorem. And then all you do is divide X here by this number. And then at that point, you have a unit vector.
So this one works for Raman data, right?
Yep, you can do this for Raman data. Really popular for Raman data.
Okay, thank you.
Yep. So this is kind of the standard notation that people use in scikit-learn for pre-processing. I prefer to explicitly do the math myself using NumPy. So I will actually go through and do something like take, let's see. So I will go for, so implementing this by hand. So I will say for x underscore I in x. So basically I'm going to take each row here in the data frame and process each of those by itself. I'll set up x underscore normalized Luke as a blank array here. And then I will say xi norm is equal to np dot square of xi. And then I want the sum of that, and p dot sum of this. Oops. And then I would also want np dot square root of this. And instead of doing that, I would just go I would append this to that list that I'm making here. So if I run this, maybe I need to import NumPy as NP.
And so what does happen here?
Right. So instead of doing this process here, which uses like a normalizer that's built into scikit-learn, typically I like to do this normalization and pre-processing by hand. So I know like exactly what's happening to the data, because there's a lot of moving parts that are happening in the background of these normalizer functions. And like if I program it this way, then I have absolute control over everything that's happening.
Yeah. So, but just the happen itself, why did you add the happen? What does this function?
This here? Oh,
Yeah,
dot
look,
append?
dot append, yeah.
It appends this value to this array here. So basically I initialize an empty array, and then as I loop through each of the patients, I just append this new value to it.
Okay, sure. Okay, perfect. Thank you.
And it looks like NumPy does not have a module called square. Let's see. NumPy square of each array element. Let's see, this is how I do np dot square. All right. That was UARE. Maybe this will work. Okay. So if I have normalized X, I'm hoping that my one that I made here is similar. Oh no, I did a bad job.
I think you need to divide each element by this normalized factor.
Yes, you're right. Okay. Yeah. So my norm factor is equal to this, right? And then I want to append xi divided by this norm factor. You are right. Okay, let's see if this works. And I want to, at the end, since I have a list of NumPy arrays, I'm going to say that's dot as equals this. So basically my last step here is taking that list of NumPy arrays and just turning it into a regular NumPy array. And let's see if what I did looks the same. Yeah, how about that? All right. That looks like the first row there. That worked pretty good. I didn't expect that to work right away. Thank you, Masa, for picking out my error. You were totally right. Okay. So I really like doing it in this way because I like having control over it. But if you're really confident in how this works, I mean, this is really readable. And when I read this, I'm like, I kind of puke in my mouth a little bit. It's not that great. So if I write it, I know what it is. But if somebody else is reading it, like I'm reading this guy's code, then I know exactly what's going on here. You can, if I move to the next one, you can standardize the data. So the syntax is basically exactly the same, where you define a scalar on the data and then you transform the data with that scalar. This one uses standardization. So this standard scalar, so it does a zero mean with a standard deviation of 1. And then binarization will basically either assign a value of 0 or 1 to everything. So this is kind of interesting. And I assume we'll probably destroy this data set. Yeah. So this is your X matrix over here. Then the binarized X matrix ends up looking something like this. Not super useful here, but where that can be useful is, say, like the output of your neural network for a classification problem may not be exactly 0 or 1, and you're going to have to round out those results to either an actual 0 or 1 to assign a label to it. So that's pretty much it there. Rescale data. Oh yeah, so the min-max scalar, this is a good one. So essentially what this does is it rescales the data so that the minimum value is 0 and the maximum value is 1. So this does, I'm just going to do this in a comment. Data is equal to data minus the min of data. So that's, this part here is 0 is the data, so that the minimum value ends up being 0. And then it also normalizes it by the max of data minus the min of data. And this is a really standard kind of scaling operation that happens. You can do this in 2 steps, where you first 0 it and then you get the max of that new array. But if you want to do it in 1 line, this is essentially what this scaling method is doing. Let me just take a peek at what the next chapter is saying here. Yeah, so it looks like the next one here, we're starting to do feature selection. So I think that going through 7 chapters is quite a lot to start with for our first lesson. So I'm going to stop it there and just open the floor to any questions that anybody has. Okay, looks like you're all experts at scaling data and importing data into pandas. Oh.
Are these edits or comments going to be saved in the Google Drive?
Yeah. So I'm directly editing these over here. So if we go into Machine Learning Grant Lab, you should see this Luke Python scripts. And if you go into, particularly, which one was it? Was it the normalized data? Yeah. So in normalized data over here, and this is chapter 7 that we're in. You can open this with Notepad, I guess, and you'll see my edits directly in here. So you can go ahead in there and have a look at any of the things that I'm doing. I'm always going to work out of that directory so that you'll have access to everything.
question, Lewis. Hey. Can you hear me?
Yep. Yeah.
Oh, I can't. Oh, I got headphones. Okay, I can hear you.
All
Hey,
right.
I got a question.
Sure.
Did you need to get a COVID test to fly to Toronto?
No, no, I didn't. So domestic travel, you don't need it.
Okay, cool. I was just wondering.
Yeah. That's it. Yeah, I gotta get one for traveling to Detroit over the weekend. So I have that booked on Thursday. So it seems like the deal is that you can use the rapid antigen test to get into the US, but Canada only accepts the PCR test on the way back. So if I have to get the PCR test anyways, then I'm just gonna get that one.
Cool. Yeah, I got to figure out where to get mine from.
Yeah. Okay. So I'm actually flying back to Toronto on Monday next week. So we'll take a break next week and we'll come back to it in the week after that. Okay. And I'm gonna stop recording this here. Let's see. I think my computer is gonna go crazy trying to convert this video. Okay, stop recording.